let's look at the next lecture. Now, this is still part of the topic, section 2.5, continuity. It's the second part of it, the intermediate value theorem. It's a theorem whose prerequisites involve that a function be continuous. So remember that a function is continuous at a point if the limit as x approaches that point, that x value of your function, equals the function defined at that point. And remember that a function's continuous on a closed interval if it's continuous at all at all x values on the interval, right? Closed interval, right, meaning that the endpoints are in the interval, right? So this is an important theorem. You don't need to memorize the theorem statement, but you do need to know what it means, right? You need to know how to use it, right? It says that if we've got a continuous function on some interval, let's say a to b, doesn't matter where a is, right? And this is our x-axis, this is our y-axis, right? And maybe it doesn't start where it ends. Maybe it starts here, I don't know. And maybe it, I don't know, something like this, something like that. I don't know. Maybe it does something like that. Okay? Then what that means is, right, so it starts at f of a, right? That's the y, looking at it from the y value perspective, right? That's f of a. This is f of b. What that means is that f passes through every possible y value, right? Every single y value you could think of, maybe like this guy, for example. There's some x value c such that f of c equals that y value. In particular, it's used often to show that it crosses through the x-axis at some point, right? So again, the exact statement is written right here, and you should read it. You can pause the video if you want. But that's effectively what the statement means. Now, why is this important? This is actually very, you might be thinking, well, this is very obvious. I agree. It's actually pretty challenging to prove, believe it or not. But it's very important because it means that a solution can exist to certain equations that might be very difficult to solve. But because those equations can be rewritten as continuous functions, all we have to do is show that, well, if we start down here and end up here, then we've got to pass in between them at some point. For example, is there a value c such that sine of c equals 1 over e? Now, if you remember your trig, you might know that that weird number e that came up, that doesn't really work well with trig functions. Like, there's no nice value, there's no nice angle that gives you sine of that angle equals 1 over e. However, I'll say let f of x equal sine of x. So f is continuous everywhere. Okay? So we know that since sine, I'll just say, you know, f of 0 equals sine of 0, which we should know equals 0. And also, let's think. We know that 1 over e is positive, right? Okay. And we also know that f of pi over 2 equals sine of pi over 2, which equals 1. Then by the intermediate value theorem, there's some c, and we actually know that it's in the interval 0 to pi over 2, right? 0 to pi over 2, such that f of c, which equals sine of c, equals 1 over e, right? Because 1 over e is between 0 and 1, right? right? I'll let you make an analogous argument for cosine equaling that there's some d such that cosine of d equals 1 over the square root of pi. It's completely analogous to what I just wrote. Now, recall that the solution to an equation is a value r such that f of r equals 0. Remember that the root of a function is a value r, we'll call it a function f, is a value such that f of r equals 0, right? So I might use the word root or solution kind of interchangeably. If we're talking about an equation, I actually should have said solution, right? If I'm talking about a function, we can talk about root. Or polynomial, we talk about root. If it's an equation, then it has a solution, okay? So anyway, show the equation as a real solution. I'm not asking you to solve the equation, right? You can factor a cubic. It's a nasty formula. I don't even know what it is. But we're not trying to do that. We're just trying to show a solution exists. So all we need to do is come up with a continuous function that is the cubic, show that there's a value below 0, a value above 0, and then use the intermediate value theorem to show a solution exists. So what we're going to do, we're going to say let f of x equal our polynomial. So f is continuous everywhere, right? Okay, so I guess I'll just say since f of, I don't know, I need some value, right? You see, I'm trying to show that the equation equals 0. I'm trying to show that our graph looks something like this, and that there's some value, some x value, where y equals f of x equals 0. I don't know what it is, but I just want to show it exists. So I need to find some value that gives a negative value, right? So maybe, I guess we know that f of 0 equals negative 2, and that's less than 0. And f of, is f of 1 greater than 0? No, it is not. I guess we have to go to f of 2, right, which equals, 4 times 32, minus 24, plus 6, minus 2. It doesn't really matter what it equals, it just needs to be greater than 0. It's clearly greater than 0 by the intermediate value theorem. There's some c in the interval 0 to 2 such that f of c equals 0. All right? So that's what we do. So note that this problem, it's not like a problem-solving technique per se. This is more we're writing a proof. We're showing the existence of a solution. We're not even finding the solution. So this is a little bit different, but it is a bit formulaic. Okay? Now let's consider example 4. Does this equation have a real root in the interval 2 to 4? Well, you can try using the intermediate value theorem if you want. You can pause the video and try. But first, you need to verify that the intermediate value theorem holds. Well, one thing to keep in mind is let's let f of x equal x squared plus 7x minus 30 or this, right? Now, if we take a look, we can actually factor the top and the bottom, right? This is going to be x plus 10 times x minus 3, and this is going to be x minus 3 times x minus 3. So you notice that something cancels, right? The x minus 3's cancel, but hold on a sec. We can't divide by x minus 3, right? F is not continuous on the interval from 2 to 4. So we can't use the IVT on the interval 2 to 4 to guarantee a root of f. in that interval, right? Because f does not satisfy the condition of being continuous on our interval. Maybe I should say it's not continuous on the closed. I guess we do need the closed interval from 2 to 4. But so be a little careful, right? So anyway, to answer the question, no, it turns out f has no real root in 2 to 4, right? You might think, oh, it's got to be x equals 3, but actually no, f of 3 does not exist. All right, and when you cancel it out, you can pretty clearly see there's no root, right? So not only can you not use the intermediate value theorem, this doesn't violate the intermediate value theorem because you couldn't use it in the first place. All right, let's take a look. Show that this equation has a real root. Well, again, same thing as before, right? Let f of x equal your function. Right? F is continuous everywhere. It's a polynomial. So, since f of, I guess I'll just say, since f of 3 equals negative 3 cubed plus 17, which equals negative 10, which is less than 0, and f of 0 equals 17, which is greater than 0, by the intermediate value theorem, there's some c in the interval 0 to 3 such that f of c equals 0. So f does contain a real root, right? So this equation does have a real, again, I should be saying solution. Okay? So this guy has a real solution. Okay. This one is quite challenging. It's not super challenging, but it takes a little bit of work, right? Well, is it that bad? No, it's not that bad. This is not super challenging. Still, I'm gonna let you try it. Sorry, I got this confused with another one. No, try that one. Just try that one on your own. You know what? Actually, no. No, I'll do this one. This is not so bad, right? Here, you can do this one of two ways. You can let f of x equal 5x squared plus sine squared of x, and then show that there's a value less than or greater than 14. Or you could just subtract 14 and then do the same thing we've always been doing at 0, right? So anyway, f is continuous, right? It's continuous everywhere, right? So let's see. I guess we can say it's going to be tough to evaluate this function, but I guess what you could say is since f of 0 equals, well, it's going to be 0 plus 0 minus 14 equals negative 14, which is less than 0, and f of 10 is going to be greater than 0 by quite a bit, right? This is going to be 500 plus, we know this is going to be bounded by negative 1 and 1, so no matter what, we're greater than 0. By the intermediate value theorem, there's some c. In fact, there's some c in the interval, 0 to 10, such that f of c equals 0. So 5c squared plus sine squared of c equals 14. All right, that's all we got. Whoops.